What we're going to do now is have a look at some modeling, which is essentially real life or worded scenarios that we're representing using trig functions here. Now, what I'm going to do is show you a live thought process and problem solving process, because I haven't looked at this question, haven't done this question. I don't even know what part A through to E is even asking me. And the point of that is I'm going to see on the fly whether or not derivatives is the best choice to answering that question, or maybe transformations are the best choice of answering that question. Because the reality is it doesn't matter which way you choose, as long as you choose a relevant technique and you show you're working or you're thinking. Let's get into it. So while out on his trawler, John North, a fisherman, notes the height of the tide can be found using this equation. So H is meters, that's the height of the tide, and T is the number of hours after midnight. Okay, so T is 3, it's 3 a.m. Yep, easy peasy so far. Now looking at this equation, the first thing I'm seeing before I even work out what the question's asking me, looks like I've got an amplitude here of 2. Okay, I've got an A value right here. I've got this K value, which means that's my equilibrium point. It looks like we're 5 meters deep and we fluctuate either side of that. All right, knowing what our transformations do, my equilibrium's at 5 and I fluctuate up and down above that. So straight away, that's telling me, just looking at those two numbers, my highest height is going to be 7 and my lowest height is going to be 3. Just using those two transformations. And I've got a B value here. So my B value is going to affect my period. Now, I haven't got a H value. So straight away, I know it's a cos function. I know what a base cos function looks like. And I know that a base cos function always starts at a maximum. So in this case, it's not reflected. So that means I am starting at a maximum. And I'm not slid left or right with a H value. And if I'm not slid left or right with a H value, yeah, I'm going to start at a maximum too. So I'm going to have a high tide at midnight, and then I'm going to have high tides later on, and I can probably use my B value to work out my period and when the other high tides might be. All right, now let's get into the questions. This is just me looking at the equation so far, just thinking. All right, part A, here we go. Determine the height of the high tide and when it occurs in the first 24 hours. Okay, when it occurs in the first 24 hours. Well, high tide is A plus K, which is 7 meters. So I'm just going to use transformations for that. That's nice and easy, right? That's easy peasy. There's other ways that we could do it, but I think the transformation way is definitely the fastest. That's the height. Now the question is, when does it occur? Well, let's quickly go over here and use our B transformation. Period is going to be, it always starts with 2 pi, but we're going to divide that by pi on 6. So 2 pi divided by pi on 6 is the same as 2 pi times 6 on pi, which is the same as 12 pi over pi. Oops, 12 pi over pi. And these pi's are going to cancel out. So what I'm going to be left with is a period of 12. And in this case, well, that clearly means hours. So what that means is, if I did a quick little drawing of this, I'm going to start at a max, and then I'm going to go all the way back until we get another max. Now that's the first 12 hours. It's asking me about the first 24. I'm going to do that again until I get another max. So we know we start at a max, we have another max, and then we're going to have another max. Again, this is just me using my idea of transformations. So times R. T equals 0. Then one full wave happens after 12 hours. So T equals 12. Then the next full wave is going to happen up here after another 12 hours. T equals 24. So far for me, transformations is the easiest way. Let's look at B now. Determine the difference in height between the high and low tides. Oh, okay. Well, max equals 7. The minimum is going to be 5. The minimum is going to be at K take A. So 5 take 2, so 3. Therefore, difference is 4 meters, which is basically from 3 meters up to 7 meters. Nice and easy so far. Again, just transformations. Sketch the graph of H in the first 24 hours. Oh, well, we kind of did that already, so let's just do it neatly. Here we go. Part C. Where am I going to move this? I'll put my x-axis down a bit lower. I'm now going to put an equilibrium line up nice and high. My equilibrium line is up here at y equals 5. That's my equilibrium. That's my EQ line. And I'm going to go all the way up to 7. I might even move this up a bit higher. So I'm going to be starting up here. I'm going to go either side of this wave. And then, as we saw, I'm going to do it again. So we said these maximums are going to be at 0, 12, and 24. We also said these maximum heights are 7 meters. Now, let's just think logically about our minimums. The minimums are halfway between the maximums, so they're going to be at 6. Then this one's going to be here at 18. And we saw before from transformations, and our minimums are 3 meters. The only other points we'd need to know are these points. Now for every single one of these points, they're all at the equilibrium line. So they're all at something and 5, something and 5, something and 5, and some sort of x value in 5. And again, what's that x value? Well, now it's halfway between the max and the min. Halfway between 0 and 6 is 3. Halfway between 6 and 12 is 9. Halfway between 12 and 18, we're going to be up here at 15. And halfway between 18 and 24 is going to be at 21. Done. We have completely sketched this. The only thing we'd need to improve upon are our axes labels, where this is T. So this is T in hours, and our y-axis here is H in meters. All right, now part D. John North knows that his trawler needs a depth of 6 meters to enter the harbour. Determine when he's able to bring his boat back into the harbour. All right, so visually, let's just have a look at shading this. So I'm just going to say D. We're going to look at just visually, where does that look like on our graph? Well, somewhere bigger than 6. So here, roughly, here, and somewhere here. That's roughly the zones that he is able to enter. Now what that means is, when is that function equal to 6? So those points where his function is equal to 6 will be here, 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 here. There's quite a few points. Now of course, a question like this is starting to become calculator based. So let's have a think about what this might look like, and can we solve it without a calculator? Okay, so what we're really trying to say is, when is this equation of 5 plus 2 cos pi on 6 t, when is that equal to 6? Well, let's start rearranging it and see if we can work it out. Well, 2 cos of pi on 6t is equal to 6 take 5. So 2 cos of pi on 6t equals 1. and I'm going to move that 2 over. So cos of pi on 6t equals a half. So this is where I'm going to slide this across now. Let's be thinking, where is cos equal to a half? And the easiest way to think about that is a combination of a quick sketch of the unit circle. Oh boy, better look better than that. A quick sketch of our unit circle. 0, pi, pi on 2, and 3 pi on 2. And of course, we're talking about a half, so we need to be thinking about one of these triangles. I'm going to start with the 60-30 triangle. Right. So let's think about this. Where is cos equal to 1/2? So what angle do I have to pick in this triangle that my adjacent and hypotenuse, that's what cos is, right? If we think about this, cos is just adjacent over hypotenuse. So what angle do I have to pick that the adjacent and hypotenuse makes 1/2? Well, I would pick this angle. If I'm picking this angle, then my adjacent is 1, and my hypotenuse here is 2. So that means my angle is 60 degrees. But of course we don't work in 60-degree land. We need to think, what is 60 degrees in terms of radians? 60 degrees in terms of radians is pi on 3. So, is that the only place that cos is going to be a positive? Well, no. Cos is all about the horizontal direction. So my answers are positive 1/2, so I need to be in the right quadrant. So I am going to be up here at pi on 3, but I'm also going to be down here at pi on 3 below, but it's not pi on 3 below, it's all the way around. So I would be at 5 pi on 3. So there's 2 locations in one revolution here that allows me to get an answer of 1/2. So maybe there's more. Maybe we do even 2 or 3 circles of this, and we'll see what happens. So what does that mean? What does all of this mean? It means, I'm going to switch over to green now, when this bit on cos is equal to pi on 3, you get a half. So when pi on 6t is equal to pi on 3, then you get an answer of a half. Because when you do cos of pi on 6, it's the same as you doing cos of pi on 3. And all we got to do is rearrange. T equals 6 pi over 3 pi, which is just 2. So my first part I'm seeing up here is this very first location must be 2. That's the first point way up here on my graph. So I'm going to put 2 and 6. I might actually do these points in yellow to make it a bit easier to see. So here, 2 and 6. Well, clearly we need to keep going. Well, let's have a look if I did the rest as, well, when is pi on 6? T equal to 5 pi on 3. And again, we rearrange. 30 pi over 3 pi. Well, 30 divided by 3, pi divided by pi, 10 hours. Well, that must be that point there. Right? So that bit there must be 10 hours at 6 meters deep. And what we'll start to know is there's a bit of a pattern. Well, the next pattern is we're probably all the way back up here. I'm going to now keep going. If I was to keep going all the way around the circle and I went back up here, we would now be at 7 pi on 3. So I'm going to solve that one. Let's keep going with that one. Where is pi on 6? T equal to 7 pi on 3. Well, rearrange that again. 7 times 6 over 3 pi. 42 divided by 3. 14 hours. So again, we're back up here and we'll be at 14 and 6. Alright, what we're starting to see is the gap from somewhere like this to somewhere like this, because the wave is a wave, it's a pattern, right? That gap to that gap is an 8-hour gap, which means from 14 up to here is also an 8-hour gap. So we're going to be at 22 and 6, and we've got the only other point. So let's now have a final look at what D was asking us. When is he able to bring his boat back in? So here we go. Boat can go back in. Boat back in. When T is less than or equal to 2, comma, when T is between 10 and 14, equal to on both, and lastly, when T is greater than or equal to 22. Now, of course, the first one and the last one could be a little bit controversial, because as we know, our domain is limited from 0 to 24. So maybe they're also looking for that T is between 0 and 2, T is between 0 and 14, and T, oopsies, and T is between 22 and 24. So maybe they would prefer that. I think the last option is probably the safe one, but using our common sense, obviously, this is usually much quicker to write. But of course, we never know how picky someone at QCAA is going to be. All right, almost there. Part E. Determine the rate of change. All right, pause. Rate of change. Derivative. Straight away. Derivative has to be derivative. I'm going to grab out my green pen for this one. Here we go. E. Determine the rate of change of the height. Okay, rate of change of the height. So that's going to be dh. Oops, it's a little h. dh dt. Rate of change of the height when he first brings his boat back into the harbour. First brings his boat back into the harbour. Well, I mean, he can bring his boat back into the harbour when it's above a certain time. So looking at that map there, let's just go with T is 10. Let's go with T is 10 hours, just because it doesn't make sense that if he's leaving at midnight, that he's going to want to come back in after just 2 hours, or like leave and then be back within 2 hours. Doesn't make sense. So let's assume he can bring his boat back in at the 10-hour mark. So we're going to go dh to t at t equals 10. So dh to t is equal to, so what is the derivative of our base function? Well, this is my function up here, remember? I've got to do the derivative of this function. So, as we know, h is equal to, just shimmy this down a little bit, h is equal to 5 plus 2 cos pi on 6t. Well, the derivative of cos, negative sine, Disc Dickens. The 5 goes away. It's going to be derivative of cos is negative sine, so negative 2 sine. I don't touch anything in here. Times by the derivative of what's inside my bracket. And then I can tidy that all up to be negative 2 pi on 6 sine of pi on 6t. And of course we can tidy that up even further to be negative pi on 3 sine pi on 6t. Now what I still haven't done is substituted in that t is 10. So let's substitute that in now. So what we're going to have is negative pi on 3 sine of 10 pi on 6. Now let's think about where 10 pi on 6 exists. Well, 10 pi on 6 is the same as, this is the same as negative pi on 3 sine of 5 pi on 3. So let's go back to our circle over here. 5 pi on 3. Well, we know exactly where 5 pi on 3 is. So 5 pi on 3 is a base of 60 degrees. And if cos is adjacent over hypotenuse, then sine is opposite over hypotenuse, which is root 3 over 2. So negative pi on 3, sine of 5 pi on 3 is root 3 over 2. All of this here becomes root 3 over 2. The only question we've got to ask ourselves is it positive? Is it negative? We know the magnitude. We just got to know, is it positive or is it negative? Well, let's have a look back up here again. We saw before that cos is all about the horizontal, and whether we're in the right hand or the left hand quadrants, cos is, or sine, sorry, is all about the vertical. So are we in an upper quadrant or a lower quadrant? Well, we're down here at 5 pi on 3, so that's a lower quadrant, which means we are at negative root 3 on 2. And of course, we can multiply things, cancel some things out, and my negatives will cancel out as well. So what we're going to have is pi root 3 on 6. So to h to t is equal to pi root 3 on 6. Now, that's obviously not a very nice number, so if this was a real world question and you had your calculator at your fingertips, let's probably make that actually contextualize. So it's positive, so let's put it into real words. That means the water level is increasing by, so increasing, positive number, and we'd put that in our calculator and try to get a decimal so we can talk about it. If we put that in my calculator, the answer is 0.1, and it's meters with respect to time, which is hours. So that means we are increasing by 0.91 meters per hour. All right. So what you've just seen is, the first thing I like to do is just quickly analyze what my function's doing, just very briefly. And if I can, we practice so much of transformations that we can use it to answer our questions quite quickly. And then at the end here, we're going to use our derivative to solve the problem. Now, one thing I want to point out real quick is we didn't have to use transformations for part A. Part A says the height of the high tide. That is the maximum tide. And as we know from derivatives, if we ever want to find a max and a min, we can simply derive and solve for when that is equal to 0. Okay, so let's just quickly have a look down here. We derived it before. We've derived this. Here we go. Here it is. That's the derivative. So the simple question is, where is that derivative equal to 0? Well, where is sine equal to 0? On a unit circle, right? On a unit circle, where is sine equal to 0? Well, at 0, at pi, at 2 pi, they're all the locations where we're equal to 0, which means they're all of the maximums, right? And we could have used that sort of technique if we really wanted to, right? I think that sometimes derivatives in solving it that way is often a little bit slower and honestly a little bit more difficult for no reason when you've got a strong grasp of transformations.